inequalities, right? And then we went on to cover what is called the Chernoff bound, which was a strengthening of Chebyshev's inequality for the particular case of independent samples. And we use that to compute sample size, especially in this opinion poll kind of situations. Then we also looked at continuous random variables, which is so you have continuous random variables, and then your normal PMF doesn't make sense. So we defined this new function called PDF, probability density function, which can be integrated over various intervals. And we also looked at what is called the cumulative distribution function. And finally, we also saw few examples of continuous distributions. One is the exponential distribution. Then there is the normal distribution. And of course, we saw the uniform distribution in real numbers in an interval. Okay. So let's today's lecture we'll solve some exercises on these things. We'll solve more problems on this to get some more confidence about this. Okay. So let's get started. This is a common problem which occurs in computer science. Okay. So you have a AI agent. The AI agent, if you ask anything, there is some probability. Okay, the AI agent will say yes or no. Okay, and for each question, the AI agent lies probability 1/3. Probability 1/3 it will select. So, hello. I'll just mute everybody other than myself. Okay. So if you have a question, you need to unmute yourselves and ask. Okay. Okay. So so this is a common problem in computer science. So you have a agent which is not completely. It has some. It makes some mistakes. Okay. It might. I mean, many times this happens. That okay. The agent will not give the correct answer with probability 1/3. But gives the correct answer with probability 2/3. Now we have access to such an agent. We need to devise a method to get the correct answer for any question with probability 99%. So how would you do this? You need to unmute yourself and speak. How would you do such a thing? I mean, the agent is only slightly. So another situation this happens is again testing for a disease, right? You have a test and the test will give you the correct answer only with probability 2/3. Probability 1/3 it won't give you the correct answer. But you want to get the correct answer with probability 99%. So what should you do? Nobody wants to give a try? Hope you can hear me. Hello. Please unmute yourself and speak if you can hear me.
Yes, sir. We can hear you.
So what should be done like in this situation? How would you devise, how would you find? Nobody has a clue. It's a very common thing that you do. I mean,
so we will make tree and decide.
We will make tree and decide. Okay. What do you mean by tree? Sorry.
As we have previously done that, we have to make it a probability probability of 0.99 correct now.
Yes.
So we have to make tree that it is lying or it is not lying, and then we are getting correct or not.
Yeah, but the probability of correct or not is already given 1 by 3 and 2 by 3. But we want to boost this 1 by 3 and 2 by 3 to 0.99 and 0.01.
So we could use the Markov's inequality or the Chebyshev inequality.
I mean, first of all, what will you do physically? Then we can come to the analysis later.
Sir,
First,
can we ask multiple times the
yeah.
same question?
Yeah, I mean, we ask the same question multiple times. If your test is faulty, if you have faulty kit for testing, you just independently use multiple kits for testing, right? That's the common sense of doing it, right? Yeah, you will be using multiple kits for doing testing of a single person, but you test him independently with multiple kits. Yeah, yeah. So maybe individual kit has only 2 by 3 probability of saying whether it is correctly saying whether it is, yeah. But now what should I do? So I just asked say some n questions. Yeah. So ask same question n times to the agent. Same question I asked n times the agent. Yeah. Now what should I do? So let's say the answers of the agent is x1, x2 up to xn. Yeah. Xn is a binary random variable 0, 1. Yeah, the agent says yes or no. Now what should I do? Yeah, let's take that common sense forward. Like, yeah, you need to ask multiple times, and then you do what?
We can use linearity of expectation, so 2 by
No, no,
3 and
no, let's not come to the mathematics first. Let's come to have a common sense solution. Okay, Raman said that, okay, we will ask the same question multiple times, and then what should we do?
Then we should take the mode of the answer. I mean, the
We'll take the
maximum.
majority answer. Yeah.
Okay.
The majority of x1 to xn is 1. I will say 1. The majority of x1 to xn says 0. I will say yeah, 0. That is our algorithm. Yeah, is the algorithm clear? What is the common sense way of doing it? Yeah. And now we can analyze it. Yeah, so whenever you look at a problem, don't jump into probability. First, understand the problem and try to make some common sense solution to it. Yeah. Once you have a commonsensical solution, here the commonsensical solution is as Raman said, just ask multiple times and look at the majority answer. This has no probability in it. It's like common sense. Yeah. Once you have that common sense, we can start analyzing mathematically what that common sense, the analysis of that common sense is. Okay. So always there is this two step. Whenever you have a problem, you use your common sense, come up with a solution. Yeah. And analysis is the second step. And both the steps are essential. Okay. We shouldn't jump into the second step. Maybe because our approach itself might be wrong. Okay. Yeah. So how would you analyze this? Yeah, I mean, how would you analyze this? So let's define xi. Yeah, xi is the random variable. Is answer to ith query is correct. Yeah, so if it is correct, it will be 1. Otherwise, it will be 0. Is that fine? Xi is the whether the ith query is correct. I mean, the reply to the ith query was correct, and otherwise it is 0. Yeah, and yeah. So what will we do? We will just look at. I mean, so if we say the majority, so we already answered this part. Yeah. Now question is, how do you get 0.99%? how large should n be? Yeah, is n equal to 1000 fine? We don't know. Yeah, and that's exactly what the problem is asking. Yeah. How many times should we ask the agent so that I can get the answer with confidence 99%? Yeah, so how do you analyze this? Yeah. Any ideas? So what is the probability that you get the correct answer? Probability that your approach gives you the correct answer. Yeah, what is the probability that your approach gives you the correct answer? That is the probability that summation over xi is greater than or equal to n by 2. The majority of the answers were correct, then our final answer using this approach is also correct, right? So this is the probability we want to compute. We want this probability to be 0.99, right? This is what we want, right? Is there a question regarding this? This is what we want. Yeah. How large should n be such that this probability is greater than 0.99? Yeah. Yeah. Is there a problem with this approach? Can anybody think of a problem with this approach?
Sir, how will we understand that whether the agent is answering correctly or not?
We don't. We won't. We won't know the value of xi, but I am just analyzing it. Like
Okay.
even earlier in the sample size thing, we didn't know the value of mu or anything like that, but we can still mathematically analyze it and find the value of n. If you remember the opinion polls question also, we had the same problem. We don't know mu. Mu is what we want to find out. Yeah. But we still were able to analyze it. We can still mathematically analyze it. Yeah, I mean, okay. So, but is this statement clear that this is the question we are asking? How large should n be such that summation of xi is greater than n by 2 is at least 0.99? Yeah. And I'm saying there's a problem with this probability also. What is the problem? Yeah, so you need to take care of ties also. That's all. Okay. I mean, if n is an even number, there's a problem here, which is okay. 50-50. The agent said right now we are considering that even if 50-50, you will say okay. I mean, yeah, there's a problem here when it's 50-50. So n has to be odd also. Okay. Otherwise, there will be a problem here. Is that clear?
Why we are taking n by 2? Yes, I am not getting this one.
So what is our commonsensical reasoning? Yeah, our common sense reasoning is we will take the answer given by majority of the people. In the majority of the thing, what is the correct answer that we will give? Yeah.
Yes, sir.
Yeah, and this procedure, when does our procedure give you the correct answer? When majority of the answers to the majority of the questions were true.
Okay. So, working the value n greater than or equal to n.
I am just saying that we have a procedure, okay, for finding out the correct answer, which is you ask the question n times and look at the majority answer. This is our procedure. Okay? And when is our procedure 2? When majority of the answers were correct. That is, xi is the random variable says that ith query is correct or not. Yeah, correct. Then 1 and 0 otherwise. Yeah. So when summation of xi is greater than or equal to n by 2, then the answer we give is also correct. Yeah, I'm just. Yeah, you should also think in terms of that common sense. If you just think in terms of mathematics, this will be extremely hard. But if you also need to think in terms of physical situation and the common sense algorithm. Okay. Yeah. So if you have convinced yourself that this is the what we want, yeah, how would you analyze this?
Sir, I have a doubt.
Yes.
Sir, if n is odd, wouldn't it be sigma of x is greater than n by 2? Like if n is 5, then sigma of xi should be greater than 2, not greater than or equal to 2.
Yeah. So I should say it has to be greater than. Yeah, you are right. You are right. Okay. Yeah. So yeah. So this is the probability we want to analyze. So how do you analyze this probability? How do you find out the value of n such that this happens? Yeah.
Sorry, sir.
How do you find out the value of n such that this happens?
We can do 1 minus CDF.
Anybody else have a idea? Thought I saw a hand up. So how do you analyze this probability? We only know Markov, Chebyshev, and Chernoff. Yeah. So what is the expected value of summation xi? What is the expected value? What is the probability that xi equal to 1?
2n by 3 expected value.
Yeah. This is 2 by 3 and this is 2 by 3 times n. Yeah, everybody agrees. Yeah. Yeah. And here remember what you want to get is probability that xi is greater than n by 2 only. Yeah, expected value is 2n by 3. Yeah. Okay. Yeah, I think earlier somebody also discussed how to analyze this. So yeah, what should we do now? What about the variance of xi? Variance of summation xi? This also we have a standard formula for.
2 by 9 into n.
Yeah,
Sir,
into 2
can you
by 3
repeat
into 1 by
why?
3.
Hello?
Yes. Yes.
Can you repeat why we got 2 by 3 n
So
and get
xi is a 0-1 Bernoulli random variable. Yeah. So the expected value of xi is 2 by 3. So sum of n independent copies of xi is 2n by 3, linearity of expectations.
Okay.
Yeah, so we only use the formulas we taught in class, nothing more.
Okay. Okay, sir.
Yeah. Yeah, so variance is NPQ. If you remember, this is actually a binomial distribution happening. All these are standard formulas. This is NP, this is NPQ. Okay, this is all formulas that you learned 2-3 lectures back. In fact, much more lectures back. Yeah, this is just a binomial distribution. All this is. So yeah, this is what it is. Okay, so how do you find this out? How do you find this probability? What should I do now? Yeah. So either you can apply Chebyshev or you can apply Chernoff. Yeah. So what does Chernoff say? Chernoff says that the probability that this summation xi, yeah, let's say we'll also divide it by n. So let's also divide things by n, such that this is 2 by 3, and the variance also let's divide by n. Then this will be there will be a 1 by n here. Yeah. And if Chernoff's bound says that minus xi minus the mu, the expected value is 2 by 3. Yeah. The probability of this greater than yeah. So if you remember Chernoff bound, this is like epsilon, yeah, is less than or equal to, yeah, it is less than or equal to 2 times e raised to minus, yeah, n epsilon squared, yeah, divided by some constant. It will be there. I am not writing that constant. Okay, so this is what Chernoff bound gives you. If you go back to the formula and check, the probability that the random variable varies from the mean by more than epsilon is e raised to minus n times epsilon squared, and there are some constants in the denominator. Okay, it will be related to 2 by 3 and everything. Yeah. So this is the Chernoff bound that we saw in the previous lecture. Yeah, and what is the relationship between this and this? What should I substitute as the value of epsilon? What should I substitute as the value of epsilon? So remember, this is exactly binomial distribution. If you remember it, it's x1 to the summation of xi's is distributed according to binomial distribution. Yeah, and if you remember the binomial distribution, you know the distribution completely. Yeah, so either none of them can be correct or all the n of them can be correct. Yeah, and you know exactly how it looks like. And the mean of this distribution is around np, that is 2n by 3. Yeah, there will be 2n by 3 is the mean. And the distribution roughly looks like, if you go over it, it kind of looks like this. Yeah. So the probability increases as you come closer to the mean, and then it looks like this. Okay. So what is this probability? So n by 2 is sitting somewhere here. Yeah. So this probability is basically the probability of this area. You agree? So this is the summation xi. This probability is probability of the summation of xi is greater than n by 2. That is this shaded portion. Now, what is this probability? This probability is. So let me just. I can draw it with a different color here. This probability, yeah, is basically x minus xi by n minus 2 by 3. That means you are deviating from the mean by a lot. Yeah, so just let's say here, here. Okay, so this space is epsilon. Yeah. And this probability is essentially this probability of this outside area. Yeah. So what should I do now? So this is asking for this probability to be at least something. Yeah. So we want the probability of summation xi less than n by 2 to be. We want this to be at most we want to be this to be at most 0.01. This is what we want. Now this quantity, that is this region, if you look at the complement of the black shaded region, that is this region, it is upper bounded by the probability that summation over xi divided by n is, let's say I take epsilon to be n by 6, minus 2 by 3 is greater than 1 by 6. Because this difference between n by 2 and 2n by 3 is 1 by 6. So the epsilon, the largest it can get is 1 by 6. So that we can still shade this region. So this is greater than 1 by 6. So this is, we know by Chernoff bound, this is upper bounded by 2 e raised to minus n epsilon squared. Epsilon is 1 by 6. So divided by 36 into 2 by 3 or something like that will sit there. And we want this number to be less than 0.01. And yeah, you just take logs. So n will be equal to, you just take logs. So log 1 by 0.01 into 36 into 2 by 3. So yeah, that's all. Is there a question?
Sir, can you explain this step?
Okay.
The second last step.
So yeah, so let me explain this figure again. Yeah. This is what we want. You agree with that? So this is what we wanted, but I am just taking the complement event. This is what we want. You agree with that?
So we are not able to see the figure.
You cannot see my screen?
Yes, now I can see.
Yeah.
Sir, the video is lagging
want.
actually.
Sir, it's lagging.
Possibly it is from your side because I am connected to the institute network. So yeah, so let me know if more people have an issue. Okay.
Sir,
okay.
it's fine.
Yeah.
And I am not seeing any issues. Fine.
Yeah. So this is what we want. I am just writing the complement event. I am just putting this sign ulta and also this sign ulta. Okay. This is what we want. Now, what is this thing? Let's draw it in the figure. This probability is essentially, so I should have drawn the figure slightly differently. Let me just redraw the figure. Yeah. So remember, summation of xi is a binomial distribution. The values it can take is 0 to n. Yeah. And the mean value is around 2n by 3. So this is 2n by 3. Yeah. So the binomial distribution something like looks like this. Yeah. And what is this region? Let me just shade this region in the graph. This is summation of xi is less than n by 2. So n by 2 is somewhere here. Yeah. And I just basically, this is the region. The area of this region is what we are interested in. Does everybody agree with that? Yeah. And
Yes.
Let's look at what Chernoff is saying. Chernoff is saying, this is what Chernoff is saying. This says that this summation xi by n deviates from 2 by 3 by more than epsilon is very small. Yeah. Let's shade that region. Yeah. So let's say, I mean, you are interested in epsilon away. So let's say this is epsilon. So it will look at both sides because it's modulus. Yeah. And which area should I shade? That is this deviation is more than epsilon. That is entire this region. Yeah. Now area of the black region is upper bounded by area of the blue region. Yeah. even when epsilon equal to 1 by 6. Actually, this distance between n by 2 and 2n by 3 is actually 1 by 6. Yeah. So I'm just I'm just upper bounding the area of the black region by the blue region. Yeah, which is, so I'm getting more area also, but that is fine. Okay, this little area also extra we are getting, but that is fine. Okay, and but this is upper bounded by this. Is that right? Is there a question regarding that? Yeah, I am upper bounding the area of the black region by the area of the blue region, and this is the area of the blue region. Yeah. And I'm also setting epsilon to be 1 by 6 because we would like this blue region to be as close to the black region. Yeah. And by Chernoff, I can substitute now. Epsilon is set to 1 by 6, so I'm just substituting epsilon there. Yeah. And you get the result n is something. Yeah. That's all we did. Okay. So now you know how many times you should ask the agent or how many times you should do a faulty test such that you can get the correct answer. Yeah. Is that clear?
This 1 by 6 came.
So what do you want to do in the figure? We would like to upper bound, yeah, the black region area by the blue region area. Is that clear?
Yes, sir.
Yeah. Now I would like to optimize the blue region area. If I take epsilon to be very small, the blue region area would be very large, and our bounds would be very bad. Yeah. So we would like to cover the black region by as small a blue region as possible. So I would like to take this epsilon. So what is the largest epsilon I can take? It is basically 2n by 3 minus n by 2, which is n by 6. Is that fine?
Yes, sir.
And 2n by 3 minus n by 2 is happens to be n by 6. So I am dividing by n, so that's why it is 1 by 6.
Okay, sir.
Okay, so that is fine. So this is a very common application in computer science. So we typically have randomized algorithms in computer science. A lot of your common algorithms that is used is randomized. And many a times your algorithms are weak. It will only give you the correct answer with slightly better than half probability. And if you run that algorithm multiple times and then take the answer, then this many repetitions, you will get the correct answer by taking the majority. Okay. So this is typically called probability amplification. Yeah, it happens not just in computer science. It's a very common sense reasoning. Happens in many fields. Okay. Whether it is in machine learning, it is called boosting. But this is a very common sense reasoning. That is, wherever you go, this is commonly used. Okay, this analysis. Okay. Yeah. Now there is a question. So we already saw that linearity of expectation we saw. Okay, if x1 to xn, we don't care what dependence they have. Summation of expected value of xi, summation over xi, expected value of this is summation over expected value of xi. This is, you can take it for any random variable, linearity of expectation. But we said, okay, if xi's are independent, then we could also write this. Yeah. So apparently you don't need it to be completely independent. Yeah. So suppose you have x1 to xn is a random variable, yeah, such that take any pair of them, they are independent. Yeah. So let's say you have 3 random variables, x1, x2 and x3. Yeah. Suppose you have a situation that take any pair of them is independent. Yeah. Then then also your variance will go as summation. So variance of x1 plus x2 plus x3 will be equal to the variance of x1 plus variance of x2 plus variance of x3. Yeah. So now you will have a question. If variables are pairwise independent, that means they are also completely independent, no? Is that true?
No, sir.
Can you give an example? Yeah. So let's say x1 is a coin toss. Okay, 0, 1, half, half. So x1 and x2 are two coin tosses, independent coin tosses. Okay, so 0, 1, half, half. Yeah, and let's say x3 is actually the XOR of x1 and x2. Everybody knows what XOR is, no? Yeah. Yeah. Now take any pair of random variables. Is x1 and x2 independent? Yeah, by definition, it is independent. I said x1 and x2 are independent coin tosses. Yeah. Is x1 and x3 independent?
No, sir.
x1 and x3 is not independent. Okay, let's see. Yeah. So let's look at the probability of x1 equal to 1 and x3 equal to. So let's draw the tree. So that here we can actually draw the tree. Yeah. So no, let's actually write it out. Probability of x1 equal to 1 and x3 equal to 1. Yeah. So what is this probability? This is the probability that x1 equal to 1 into probability that x3 equal to 1 conditioned on x1 equal to 1. Yeah. x1 equal to 1 is half. What about this? What is this probability?
Probability that x2 equal to 0.
Sorry, what is this probability?
1 by 2.
Why is this 1 by 2?
Sir, because x1 is 1, x2 should be 0 only, then only x3 will equal to 1.
Yeah, so this is the probability that x2 equal to 0. Yeah, into probability that x2 equal to 0. Yeah, this is 1 by 2 into 1 by 2. Yeah, so you can put 1, 0, 0, 1, 1, 1, all the four possibilities. You will see that it nicely breaks up into half. Okay, so x1 and x3 are actually independent, which makes sense because x3 is the summation of XOR of x1 and x2. Even if you know the value of x1, x2 is completely independently changing. So x3 is independent of x1. So x1 and x3 are independent. Similarly, x1 and x2 and x3 is also independent. Yeah. So you can have three variables. Every pair of them is independent. But is x1, x2, x3 together independent?
No, sir.
Why is that?
Because x3 will depend on the x1 and x2 both.
Yeah, I mean, if you fix the value of x1 and x2, x3 is not even it's not even random. It is something with probability 1, right? So if you take the probability of x1 equal to 1 and x2 equal to 1 and x3 equal to 1, what is this probability?
0.
This is 0 because x3 is actually x1 XOR x2, which is 0. not one. So three of them together is not completely independent. But if you take any pair of them, they are independent. Yeah. So yeah. So we will see another example like this. Yeah. So you can have a sequence of random variable. Every pair might be independent, or every three might be independent, but the entire sequence will not be independent. Yeah. So this is called pairwise independent, or in general k-wise independent random variables. Yeah, this also occurs many times in computer science, electronics, and all these things comes up, and these are very useful objects. Okay, random variables like this. Okay, so is that clear? Yeah, and if you look at the variance expression, variance expression is formed by squares, no? Yeah, and when you do squares, you will only have terms which are product of pairs of things. Xi, Xj terms will be there. But for expectation to split between Xi, Xj, you only need pairwise independence. Yeah. So if you go through the proof of variance, if you just expand the formula for variance, you will see that only pairwise independence is needed for this to happen. You don't need complete independence. Okay. So even if your random variables are not completely independent, you can still use this formula. Yeah, there is a linearity of variance if your random variables are pairwise independent, not necessarily completely independent. Okay. So yeah, I will leave you to work out the formula. If you just expand the formula of variance, there will be square terms, and then will be product of pairs. And for the pairs, you only need two-wise independence, pairwise independence for the expectation to go through, and then you will get this formula. Okay. So yeah, you should work it out yourself. Yeah. Okay. So let's go on to one more question. Yeah. So this is a very common question. So in computer science, there's a algorithms, special type of algorithms called randomized algorithms. Yeah. And what are randomized algorithms? Have you heard of it? Anybody heard of what are randomized algorithms? Can you give me an example where randomized algorithm is used a lot? Yeah. Any idea? Anyone? Okay. So randomized algorithms are algorithms which also has some randomness in it. Yeah, so that lying Alexa in the second question used randomized algorithm. Yes, agree. I agree. Yeah. But yeah, randomized quicksort. Yeah. Yeah. So there are various places randomized. So when you choose the pivot element, it's possible that you chose the wrong pivot element and your algorithm went in a direction which is taking a lot of running time. So if you had chosen that pivot element in quicksort, yeah, randomly, then with very high probability, you would have chosen something in the middle. And your the divide and conquer, both the subproblems will have almost equal sizes. Yeah. And if you do randomized quicksort, your running time is also, you can guarantee that your running time is small in expectation. Okay. So that is a very good answer. So there is other things. So if you want to check whether a number is prime or not, the very common algorithm used, which is used in practice, is a randomized algorithm. You will just take a random number less than square root 10 and just try to divide it. Yeah. And because a typical number will have a lot of prime factors, with high probability actually you can check whether a number is prime or not. Yeah. So so we will see another example. So this is a graph cut example. Okay. Graph cut. So everybody knows what a graph is, no? You are all computer science students, so you know what a graph is. A graph, if you don't know, it is a figure with a lot of circles and lines. Yeah, this is a graph. Yeah, the circles are called vertices. Yeah, circles, and the lines are called edges. Yeah, so these circles are numbered. Okay, 1, 2, 3, 4, 5, 6. Circles are numbered. Yeah, this lines, which a line will only connect two circles. Okay, so actually, yeah. So E is a subset of yeah. Basically, E is a pair of vertices, U comma V, so that U V belongs to vertices. Yeah, so everybody knows what a graph is. Yeah, I assume that you know this. Okay. Now, a cut in the graph, yeah, is a subset of vertices. Yeah, yeah, a subset of vertices. The cut defined by S is a set of edges which goes across that set of vertices. Okay, so let's look at a small example. So let's draw a very nice graph. So I like this graph because it is very easy to draw. Okay, so this is 1, 2, 3, 4, 5. Okay, so let's also put a border for it. Let's not put a border for it. This is a very nice graph. Okay. Now, a cut is a subset of vertices. Yeah. So a cut defined by S. So let's say my vertex set is 2 and 3. Yeah. So S is, let's say, 2, 3. Yeah. So the cut is a subset of edges. Yeah. Basically, you put 2 and 3 in one side and put a line like this. Let me give a different color. Yeah. So how many black lines are cut? Yeah, this 3, 5 line is cut, 3, 1 line is cut, 2, 4 line is cut, 2, 5 line is cut. So essentially the cut defined by S. Yeah, so cut, so the cut defined by S is denoted by E. So E of, sorry, not expected value, E. E defined by S and S complement is basically the set of edges. Yeah, so it is basically 2, 5, 2, 4, 3, 1 and 3, 5. Yeah, is that clear? What do you mean by cut? Yeah, so this might look like an abstract problem, but this is actually used in many places in computer science. Yeah, whether you are doing machine learning, whether you are doing yeah, computer science or cryptography, this is used all across the place. Okay, how it will be used, you will see later in those courses. Okay, so this is called the graph cut problem. Okay, you want to find the maximum sized cut. Yeah, so what you want to do is, goal is, so max cut, goal, find S such that E of S comma S complement, the size of the set is maximized. Okay, so this is the max cut problem. Yeah. So what is the cut which yeah, maximizes this? Can you tell me, is there a cut which gets you more than 4 edges? Yeah, so is there a cut which gets more than 4 edges? Nobody wants to try. So, I mean, this is a very symmetric graph. Okay, so only thing you can do is So what is this cut? This is cut is putting two vertices which is adjacent, which is like nearby in this ordering, yeah, to one side, and three things other in the other side. The cut can either have one, split 1 to 4, 2 to 3, or 3 to 2, or 1 to 4. This is the only possibilities. So if you do that 1-4 split, you will only get two edges. So if I do a cut like this, I will get two edges. Yeah. So I could also do a cut with 1 and 3 on one side and the remaining in the other side. But then I will miss this 1-3 edge. Yeah. So this is actually the maximum cut. You cannot find a set of vertices such that you can cut more number of edges. Okay. Yeah. So question is, how do you find a good cut with large size? Yeah. So the algorithm is yeah. So what you will do is yeah. So the algorithm is you will choose your set S randomly. Choose your set S randomly. So this is the algorithm. Yeah, that is, for every vertex, yeah, you will toss a coin with half probability and choose that vertex to be in the set S with probability half. Yeah, and you do it independently for all the vertices. So is the probability distribution clear? How the set S is constructed?
Sir, can you repeat once this coin tossing?
Yeah, so you have like there are these 5 vertices, no? Yeah, so now instead of choosing this S in a fixed way, our algorithm would be, so this is the randomized algorithm. Yeah. So how is a cut defined? It is defined by the set S. If I tell you how to specify S, then your cut is defined. You agree?
Yes, sir.
Yeah. So for each vertex V belong to the vertex set. Yeah. Add V to S with probability 1/2. Yeah. You just add the vertex to that set S with probability 1/2. Yeah. And basically output in the end, after the for loop, output, yeah, you can output S. This is our randomized algorithm for finding a cut, finding a good cut. Yeah, so we don't know if the cut given by this randomized algorithm is good or not. Yeah, this is one algorithm. Just randomly choose the cut. Yeah. Question is, how big is the cut? How big is, what is the size of? What is the size of given by randomized algorithm? Yeah. So the randomized algorithm is clear?
Yes, sir.
Yeah. And the question is, how big is the cut given by the randomized algorithm? So is the the size of the cut a random variable?
Yes, sir.
It is a random variable because the algorithm is randomized. Yeah. With some probability, it can be even be 0 because you choose the set S to be the set of all vertices. That happens with probability.
Sir, half to the power n.
Half to the power n. With some probability, the size of this cut is going to be 0. Yeah. With some probability, it is going to be something else. Yeah. We would like to know, okay, so whenever you have a random variable, first thing you should think about is, okay, what is the expected value of the random variable? Yeah. Yeah. So, yeah. So this is what you want to compute, the expected value of this cut given by this algorithm. Okay. So before going into that, okay, we'll first define some new random variables. Okay, so for every line, yeah, I define a new random variable x sub b. So x sub b, yeah, is 1 if the edge goes across the cut. Yeah, so I choose a random cut. Maybe I choose a red one, or I choose blue one, or some other cut. Yeah, I just randomly choose a cut. Yeah. And we will say, so there's a random variable corresponding to every edge. So every line there's a random variable corresponding to it. Yeah. So suppose I choose okay, so let me just put one more cut. I put a yellow cut also. Yeah. Yeah. So if I look at the random variable x14, yeah, so there's a random variable corresponding to every line. So if you look at the random variable x14, if I had chosen the cut red cut, then x14 is 0. Yeah. If I chose the blue cut, then also x14 is 0. If I chose the yellow cut, x14 is 1. Yeah. So is the random variable xc clear? Yeah. So are these random variables independent? Are they completely independent? Yeah, so yeah, so you can see an example graph. So if, for example, if you just take the triangle graph, yeah, you will see that there are 3 random variables x12, x23 and x13. Actually, this is like the XOR example we just saw. Yeah, so actually the third random variable will be completely fixed by the other 2 random variables. Okay, so but the interesting thing is these random variables xc are pairwise independent. Yeah, they're actually pairwise independent. You can show that. Yeah, whether one edge is part of the cut or not will not affect whether another edge is part of the cut or not, because there are 2 endpoints of an edge and you are independently choosing in the endpoints. So you need to prove this. Okay. Yeah, and if you have proved that it's pairwise independent, then this random variable y is nothing but a summation of xc. The number of edges in the cut is the number of edges which goes across the cut. Yeah. And then you know that, okay, variance, it's pairwise independent, so the variance also goes in. Yeah. So you can actually find the expected value of y is actually very easy. You can also find the variance of y. Yeah. And you can analyze the situation where the, you can use Chebyshev's inequality and actually find the probability that y is greater than at least a third of the edges. Yeah. So today's time is almost over. Okay. So we will cover this. I will ask the students, ask the TAs to cover this in the tutorial session. Okay. Yeah. So, but most of this is what you know only. Okay. You just need to work it out properly. Okay. So I can take 1 or 2 more questions before I close. So these problems are actually very important. The ones I am covering in class, that appears very commonly in computer science, machine learning, in all many fields. Okay, so looks like there are no other questions. So yeah, goodbye for today.